Welcome back, everybody. So maybe before we get started, how many people here identify as mathematicians? How many people identify as computer scientists? Okay, so one of the beautiful things that we saw this morning is that yeah, so one of the things we saw this morning is that the same thing can be described in very complementary and different ways by computer scientists and mathematicians. And one of the goals of this workshop is that we can understand each other's language. So what we're about to see is the beginning of a three-part mini course about pseudorandomness, which is, one of the real great achievements of theoretical computer science as a field. And if you're a mathematician, some words may not be that familiar to you, so please continue asking questions as we have seen in the morning. So it's my pleasure to welcome Dean Doron from Ben-Gurion University, who will start this mini course on pseudorandomness.
Thanks. Okay, so what I'll give is a very high-level view of pseudorandomness from a TCS viewpoint. I'll try to cover quite a few things, so it's not a deep dive into anything. I'll focus on the toolkit. So I'll introduce objects and techniques which we use in the area. I'll assume no prior knowledge, so please feel free to interrupt me and ask questions. So if you're not understanding, it's my fault, okay? So do interrupt me. Consequently, it will be boring for some people in the audience that I'm now seeing, so sorry about that. And importantly, hopefully it will be kind of a good opening act towards next week's bootcamp, which will feature 3 mini courses on pseudorandomness. So at some point, in many points, I will really want to talk about something, but then I'll say, no, wait for next week. There will be a dedicated talk for that. Okay, so a little bit about motivation. So we all know that randomness is very valuable. Sometimes it's essential, for example, to obtain security, privacy, to model physical systems. But even when we're not sure whether it's essential, and actually we think it's not, it's incredibly useful. That's how we often design algorithms, more efficient algorithms, maybe simpler algorithms. And sometimes, we'll see when we talk about that, efficient randomized algorithms are all we have. And for many reasons, we don't want or can't rely on perfect randomness. So this viewpoint of pseudo-randomness lets us emulate truly random processes with little or no randomness, or with very weak randomness. Okay, so in TCS, it matters a lot for cryptography to get PRGs, secret keys, secure protocols, and so on. It matters for algorithms and complexity. It lets us get efficient algorithms. It has deep connections to the P versus NP problem, to PCPs. It has really interesting connections to error correcting codes and many other areas in TCS. But it's also an incredibly useful way of thinking. We see that in additive combinatorics, number theory, learning theory. Xander will talk about structure versus randomness, where we see pseudorandomness quite a bit. In fairness, differential privacy, many areas of TCS, this viewpoint of pseudorandomness is very, very, very helpful. And Avi Vigdalsson likes to say that randomness is in the eye of the beholder. So let's take a very cartoonish example. So say some human tosses a coin, and Bob wants to distinguish between the coin being truly random and not truly random. And in this experiment, Bob cannot distinguish between a human coin toss and the uniform bit, right? But if he had all this equipment, you can almost perfectly distinguish between a human coin toss and a uniform bit. So this coin toss will not look like a random experiment. Okay.
That you'll be able to predict the
To predict, yes. So let's be a bit more specific. Throughout this mini course, we will often think of, we'll have some class of tests or observers in mind. It's just a subset. For us, it will be just a subset of all functions from 0, 1 to the n to 0, 1. And we say that two random variables a and b are epsilon indistinguishable with respect to that function class if for any f from that function class the expectation of f of a is close to the expectation of f of b. We will usually think of b as just a uniform distribution, and in which case we'll just say that a is computationally pseudorandom. Why computationally? Because it's with respect to that function class f. Okay, does it make sense? Good. Okay. So it's kind of be like the key notion we should keep in mind during those talks. Let's see an example. Most of us know and love the expander mixing lemma. I did see that Siddhant gave it as an exercise, so you should do that. So this is one way, if you kind of normalize accordingly, this is one way to view the expander mixing lemma. So say you have an expander over n vertices with degree d and normalized second eigenvalue lambda. And this is the number of edges between S and T. So for any subsets S and T, the number of edges going from S to T normalized is, you see, about the density of mu of S times the density of T up to some L. Okay, that's how we like to think of the experimental mixing lemma. Here's a pseudorandomness view. If you think of F as the indicator of a cut between S and T, it tells us that a random expander edge is indistinguishable from a random clique edge by what? By cut functions. Okay, so just so we're comfortable with that terminology. Okay, so this would be A and this would be B. Okay, those two experiments. Okay, this is a random edge. This is an expander edge. So sorry, like a random edge of a clique. Okay. Okay, so here, curly f is the family of cut functions. Okay. Does this make sense? Good. Another example, which I won't get into in detail, is Gauss sums. So we can show that the random quadratic residue is indistinguishable from a random field element by additive characters. This is for the more mathy audience here. Okay, it's also another example of function classes, in which case additive characters. Okay. Good. Good. So kind of a unifying notion that lets us actually achieve things that we want to construct is what's called a pseudorandom generator. So think of the following two processes. So process one, we have some function from a function class. Should call it curly f, so curly c. And we feed truly random bits to it and look at the distribution f of u of n versus, say you start with very few random bits, feed it to some deterministic function g that stretches d bits to n bits, and look at the distribution f of z. So we say a function g that stretches d bits into n bits is a PRG against the function class f if for any f in f, the expectation of f of z is close to the expectation of f of u, where z is just the image of the PRG. Okay, so that's a PRG, a very important concept in pseudorandomness. Right? And the whole question is, what's F? Right, so what's the F that we want to design a PRG for? Good. And another way to look at it, which I find very helpful and nice, is the image of G is just a very, very sparse subset of the entire domain that looks random for every F in curly F. So it's just like really a small number of points that have this quite magical property that they fool many functions. So for example, if kind of F minus 1 of 1 is nice enough, it's structured enough, say F is balanced, so we have the very nice property that our PRG hits roughly half of the elements of F. Okay, so this PRG indeed fools F, but maybe F is like very complicated, in which case it doesn't. Okay? So notice that it's a black box object. So the image of the PRG is independent of the function we're trying to fool, just dependent on the function class we're trying to fool. Okay? Good. And PRGs have many applications for de-randomization, for insufficient computation, for approximate counting, for explicit constructions. We'll talk a lot about de-randomization. And so for those of you who are not familiar with the notion of de-randomization, we want to convert, and we'll talk about it quite a bit, we want to convert randomized algorithm into deterministic ones with comparable complexity. So we don't want, for example, the time to blow up, and we don't want the space to blow up. We'll talk about it in more detail soon. Questions?
De-randomization, you mean reducing the randomness, not removing it?
Hopefully removing it altogether, yes. Yes. But of course, both goals are worth. Good, so which Fs are we interested in? Which Fs have people studied? So two kind of main ones for good reasons. The first one are Boolean circuits, which I'll define soon. And these have, so the reason, one of the main reasons why you care about fooling Boolean circuits is the connection to the BPP versus P question, which I'll talk about. The second one is read-once branching programs, and there are many variants, and very important and interesting because of their connections to the BPL versus L question. I'll also talk about that pretty soon. So those are two very famous families of functions. Right, I will talk about it, and also we'll talk about all of those next week. But not only them, a wide array of function classes, all sorts of polynomials, decision trees, rectangles, half spaces. You can see many more function classes. Yeah. Okay, so we have very rich literature constructing PRGs for many important and interesting function classes. Some of those we will be talking about in this mini course. Good. But you might say, well, let's take curly F to be all functions. I mean, why not? Let's get greedy. And we sometimes want that. We call that the information theoretic setting, because maybe we want our generated randomness, this output of the PRG, to appear random to any adversarial test. Maybe because we can't assume any structure, and we sometimes can't. Maybe we even do have uniform bits, but we have some adversary, and some information is leaked. It's called the site information setting, which kind of compromises our randomness, and we do need to we do want to guarantee that we fool any test. But of course, if we start with the truly random bits and then we deterministically stretch them into n bits, we cannot hope to generate true randomness. And here comes the very rich theory of randomness extractors, which we will also talk about in this mini course, and also next week Ishan will talk about it. Okay, any questions? Good. Okay. So before kind of trying to actually construct PRGs, let's take a detour and give more motivation as to kind of what are some of the interesting and important questions we have in this area, okay? And focus on de-randomization. Let's take an example, primality testing. Since the 70s, we have simple, randomized, efficient algorithms for checking primality. For example, Miller-Rabin is a randomized algorithm that gets us a certificate for compositeness with high probability. So it's what we call a one-sided AO algorithm. Okay, and please stop me, if something doesn't make sense. It's a pretty simple algorithm. It runs in nearly quadratic time. And this is n here is not the number itself, it's the number of digits. Okay? Number of digits of the number.
So what does a one-sided error refer to in this case?
Right. So if it's composite, it will say composite with very high probability, and if it's prime, it will always say prime. Hopefully, I got it correctly. I think so. Okay. So this was known since the 70s, but only decades later, the famous celebrated AKS algorithm they gave a deterministic algorithm for primality testing. The state-of-the-art implementation runs not in n squared time, but roughly n to the 6. So again, we first see that, well, we have a simple, quite efficient, randomized algorithm. And even when we do manage to get a deterministic algorithm for the same problem, it might be more complicated and less efficient. Okay? This is what we call a problem-specific de-randomization. You needed to know math in order to come up with the algorithm. And we'll talk about the scenario where we want kind of a black box way to take a randomized algorithm and transform it to a deterministic one without the need to even look at the algorithm. Okay? So it's what we call a black box de-randomization. Okay? Questions? Okay. What about finding a prime number? So say you are given n as an input, and you want to return a prime, say, between n digits and 2n digits. We're guaranteed that there's prime in that interval. So there is a randomized algorithm. You can pick a random integer in that range and check for primality, and just repeat if it's not. Okay? For primality, you can either use a deterministic algorithm or randomized algorithm, what have you. And why is it a good algorithm? Because there are many primes, right? So because primes are relatively dense, you only need a linear number of attempts until you get a constantly high success probability. What about deterministic algorithms? So we saw that there exists a deterministic algorithm for primality testing, but what about prime number generation, well, so it's an example of an algorithm, a randomized algorithm for which we don't have a deterministic counterpart. I will mention a very interesting work that gives a pseudo-deterministic algorithm for primes. I won't get into it, but if you're interested, come talk to me.
What does it mean, pseudo-deterministic?
Right, okay. I didn't want to say what it means, but I will say, since you asked, it's randomized. If it succeeds, it will give you the exact same answer. Okay, regardless of the random coins you use to run the algorithm. And this is very recent. Okay. Another interesting and very important problem is the problem of polynomial identity testing. Say you're giving two polynomials. Actually, they won't come in the form of a string. They will come in the form of an algebraic circuit, but let's assume for now those are strings. And you want to test if they're equal or not, if they're actually the same polynomial. Here's a randomized algorithm, which you would have thought about if you'd thought for a couple of minutes. Choose a random field element, evaluate both sides, and compare. Why does this algorithm work? No, you all know that. Who said that? I have the shine. Schwarzschild, thank you. Right, so Schwarzschild tells you that it will work with high probability. And deterministically, we don't have anything, in general, we don't have anything better than just a naive, expand both sides and compare, which can take exponential time. And it is one of the most important problems for which we have an efficient randomized algorithm, and we don't have an efficient deterministic algorithm. It has really deep connections to complexity theory in the area of hardness versus randomness. It's also one of the most important problem in the area called algebraic complexity. Okay, so it's yet another example for such algorithms. Good. Another example is approximating the permanent. So given a non-negative matrix A, by non-negative I mean the entries are non-negative, we want to approximate the permanent, which is just, if you're not familiar with it, it's just determinant, but take away the signs. Combinatorially, it also counts the number of perfect matching in the corresponding graph. We do firmly believe that computing the permanent exactly is very hard. Okay? But we can hope to approximate the permanent. And indeed, we have a beautiful Markov chain-based algorithm to approximate the permanent. This is the Jerome-Sinclair-Vigaud algorithm. But again, no polytime algorithm exists for that. So up until now, we've seen examples where we cared about the runtime of the algorithms. Let's see one example where we care about the space or the memory that we use to solve the problem. And the problem is graph connectivity. And let's start with undirected graphs. So we're given an undirected graph. and two vertices, and we want to determine if S is connected to T in the graph using very little auxiliary space, and I think it needs a bit of clarification. So think about your input. Your input is fixed. You're given an input, and kind of the question is, how many more variables do you need? How much more space do you need to allocate in order to answer whether S is connected to T? Okay, you cannot use the input. The input is read-only. And the question is, how much more auxiliary space do you need to use in order to say whether S is connected to T? Here's a simple randomized algorithm. Just take a random walk, right? We love random walks. Start from S, go for Polian time, number of steps. Just check if you reach T. Okay, why does this algorithm work? Because walks converge, thank you. Because walks converge in undirected graphs in polynomial time. And let's try and verify to ourselves that it uses only O of log n auxiliary space. Because in order to implement a random walk on a graph, so what do we need? We only need to store current vertex, which is roughly log n bits, and kind of make auxiliary computation that will allow us to go for the next the next step, see if we reach T. You know, constantly many number of variables. Each variable has like log n number of bits. Okay, so the randomized algorithm uses O of log n auxiliary space. This is from the 70s. And it took a lot of work. Oh, and I'll just on the way introduce some complexity classes. This puts the problem in a complexity class called RL, which is I think I'll mention it also later, but it's the class of problems solvable in O log n space randomized algorithms with one-sided error. Right? Because if S is not connected to T, you will never reach T. And if S is connected to T, you will reach T with high probability. Okay. And now, a couple of decades later, a great breakthrough result of Omer Reingold de-randomized, gave a deterministic algorithm for undirected ST connectivity using using the zigzag product in a sophisticated way that puts this problem in L, basically. The class of problems that use O log n space deterministically. So it's another instance of a problem-specific de-randomization. Okay. It's a very clever use of expander products and so on. Okay. That was undirected graphs. What about directed graphs? So in general, it's complete for the class NL. Let's put it aside, and let's care about connectivity in directed graphs that mixes fast, mixes in polynomial time. Same randomized algorithm works. So again, it's in the class RL, and it's actually, in a sense, complete for the class RL. Okay, now what about the deterministic algorithm?
And maybe you should spell out what does it mean complete.
Right. So thanks. Right. So essentially, any problem in RL can be reduced to that problem So it's kind of the hardest, it's in RL and also the hardest problem in RL. So if you solved this problem in deterministic O of log n space, you would show that RL is equal to L. Okay. So what about the deterministic algorithm for that very natural problem? We do know something very non-trivial, and this something is roughly log to the 1/2 n space. And interestingly, this is not a problem-specific de-randomization. So we actually know that RL is contained in D space, so deterministic space of log n to the 1/2 minus little o of 1. Okay. Questions?
Is it not a problem-specific derivation because it's complete for the class?
True, true. I think morally, well, you're right, but morally, I think kind of the research line was kind of the works that followed to that result. Indeed, of course, had that problem in the background, but also they're not tailored to that problem. Many of those results are PRGs, so in a sense stronger than this result. But yes, you're right. Okay. Just a couple of slides about definitions, because I was kind of waving my hands a bit. We'll be speaking about time-bounded algorithms, which are algorithms that are allowed to toss, the randomized algorithms are allowed to toss coins. And we say that an algorithm solves a language if, when X is in the language, it answers correctly with higher probability. And note that the probability is over the randomness and not over the inputs to the algorithm. And if X is not in the language, same thing. This is called a two-sided L algorithm. And if the runtime is polynomial in the length of the input, we say that the language is in the class BPP. Okay, so BPP are randomized polytime. Our language is solvable by randomized polytime algorithm. And maybe the open question in complexity theory is whether BPP is equal to P. And I'm saying D and not like, and you might say, wait, what about P versus NP? This is much more important. And you might be correct, but BPP is equal to P actually has very, very intimate connection to the P versus NP problem. Okay, so you can actually put that with the P versus NP problem. So how do we tie together the BPP versus P problem with what we saw about PRGs and fooling function classes and so on? That's kind of connect the two together. So say you're given a randomized algorithm. The input length is n. Randomness is the number of random bits is t, and it answers yes or no. It solves the language L, so it means if we consider the function that fixes the input and only looks at the randomness, it tells us that if X is in the language, the expectation over Y of that function, right, that X, Y is an input, is at least 2/3. And if X is not in the language, the expectation is at most 1/3. Right? That's the exact definition of what it means that L is solvable by a randomized algorithm. And this looks very familiar. because how can we use PRG? So recall that this is a PRG. We want to approximate the expectation of some function over the uniform distribution. Right? So if we had a PRG that fools this function class, that fools a of x for any x and for any a, what we could do is just to compute this expectation. Right? Computing this expectation is much cheaper than computing that expectation. Because computing that expectation, you need to enumerate over all y, so over all strings here. But to compute that expectation, you only need to enumerate over all seeds of the PRG. And if the seed length is like logarithmic in t, then we win. Then the blow up, the time blow up, won't be that bad. So what's the question you should ask yourself? What's the corresponding function class we need to devise a PRG for in order to fool this a of x, right? So we should ask ourselves, like, what's the structure of a of x? What separates it from like any function, an arbitrary function? In this case, the answer is Boolean circuits, which for those of you who don't know, those are just a computational model, a non-uniform one. So they get like so you put the inputs as leaves, and you're allowed to use AND, OR, and NOT gates. And there is an output. Okay. Now, any function can be computed with Boolean circuits, but what the function class we're after is polynomial-sized Boolean circuit. Okay. So we say a language is solvable by polynomial-sized Boolean circuits if for any input length n, we have such a circuit that solves the function, that solves the language on inputs of length n, and has polynomial size. Okay. Any questions for those of you who kind of didn't know about that before? Now, just a teaser, because Ronen will talk about it next week. We actually know that under complexity theoretic assumptions, BPP is equal to P, and not only that, we know that BPP is equal to P via PRGs, so we can do kind of a black box de-randomization. Okay, so every polytime algorithm can be de-randomized with a polynomial slowdown. I'm just putting the theorem here. I'm not going to talk about it in much detail, but that's just, it's like very interesting, important result. So I'll just mention it. So assuming we have some function in d time 2 to the O of n, so it's in some sense it's easy in the sense that it's in E. It's solvable in time 2 to the n, but there's also a lower bound. It requires circuits of size, say, 2 to the 0.1 n. Okay, so we have like an easiness component and a hardness component. Then, and it's widely believed to be true, then we can take any randomized algorithm that runs in time t and simulate deterministically in time poly tn. This is a result from the 90s, and we have many new results in recent years about this.
Does T have to be polynomial line, or can T be anything?
Anything. Yeah. We think of very large T's or very small T's?
I think very large. Like.
Yeah, sure.
Yeah.
Yeah, we'll have dedicated talks about this. It's called the hardness versus randomness paradigm. Good, so that was time. What about space? Again, two-sided arrow. We call this complexity class BP space, where S being log n correspond to the class BPL. And here again, we count the number of auxiliary bits needed to compute a language. So the input tape is read-only, and the random coins tape is read-only. And we don't get to keep the random coins we tossed. So we toss a random coin, act accordingly, and forget about it. If you want to keep it, you need to pay for space. Okay, so that's the model. A very interesting, more tractable open problem is whether BPL is equal to L, namely whether we can take any bounded space randomized algorithm and simulate deterministically, paying only a constant fractal block in space. Again, we believe that they are equal because it also follows from even weaker conjectured lower bounds. And unlike the BPP versus P problem, here we do have explicit results. I mentioned this result, and actually next week William will talk specifically about space-bounded randomization. And again, if we want to kind of black box full space-bounded algorithms, what is the function class F we need to fool? It turns out that it's this creature called read-once branching programs, and I won't define it now. I will define it, I think, on Wednesday. Questions? Good, yeah. Good. So hopefully I gave sufficient motivation to study pseudorandomness and de-randomization. And let's get back to our toolkit and ask, like, what are we after? Since we're kind of looking to fool the uniform distributions or distributions with a lot of entropy, we want to, it will be helpful to construct efficiently, deterministically, or with little randomness, objects having many of the useful properties of random objects. Right? We saw that, we heard that expander graphs are such objects, right? And for us, it's usually to construct object whose existence is guaranteed by the probabilistic method. Meaning, if you kind of draw a function at random, it will satisfy this property. So it's like finding a hay in a haystack. Okay? Most functions work. We need to come up with an explicit one that works. Okay? So here's one example most of us know and love. The Ramsey graph problem. Let's concentrate on the bipartite version of it. We know that any n by n bipartite graph has a k by k monochromatic subgraph for k which is half log n, even approaching log n. Using the probabilistic method, we can show that a random graph, that there exists an n by n bipartite graph, most graphs will be such, with no k by k monochromatic subgraphs for k which is 2 log n. And kind of a long-standing challenge is to find such explicit graphs, even for k which is O log n. And in recent decades, there has been amazing progress leading to k which is poly log n. I'm missing a lot of citations here because Ishan will talk about it next week. So a lot of recent work in pseudorandomness went into constructing those objects. Okay, but let's use the probabilistic method to show that PRGs exist, right? So I keep talking about that we have some function class and we want to construct PRGs for it, but do PRGs exist and kind of with what parameters? And it turns out that, yeah, there exists. So fix some function class curly f. There exists an epsilon L PRG G mapping d bits to n bits that fools the function class f with this seed length. Okay? And it's usually also a lower bound in many cases. Okay, meaning there exists such a PRG with this seed length, and this seed length is also a lower bound, usually. Okay. So I plan to just sketch it on the board. Let's see if I want to spend the time. It's like, yeah, I'll just do the beginning. It's super simple. Just want everyone to be comfortable with the probabilistic method. Right, so we have some function class f. So what does it mean that we pick G at random and we want to show that it's a PRG? So what's the probability that if we pick G at random, it does not fool the function class f? What does it mean? It just means that there exists some function such that G doesn't fool that function because G needs to fool any function. Right, so let's do a union bound. So I can enumerate over all functions and ask what's the probability that G doesn't fool f. Now, this just means that the expectation of f of G of Z for a uniform seed Z is far from the expectation of f under the uniform distribution, which I denote by mu of f. Right? So if I draw G at random, what's the probability that this happens? Now, since the outputs of G on each input are independent and uniform, those are just independent trials, and we could just use Chernoff or Hofting. And this happens with probability like e to the minus like 2 times e to the minus times 2 to the d, where d is the number, d is the seed length. So if we do like an extra union bound, because we need to take the sum over all f's, we want this to be smaller than 1, then it's easy to see that this quantity suffices. So basically, what we need to do is, if we're interested in function class, see what's the size of this function class and try to match the probabilistic construction. Okay, try to match this. It might have drastic effects if you're able to do that for curly f, which is Boolean circuits with polynomial size. But even for other curly f's, it's oftentimes very interesting and reveals many deep connections. Okay, so questions about that statement? Of course, that statement is very easy, but we need the PRG to be explicit. That's kind of the main challenge. Questions? Okay. So let's start with our first tool. And now we're kind of starting from the very basics of pseudorandomness. The first tool will be bounded independence. Let's look at this distribution. Think of each row here as just an element of this in the support of a distribution, and think about like choosing a row uniformly at random. This is just a uniform distribution over 3 bits. Okay. Here's another distribution. Clearly not the uniform distribution over 3 bits, but it does have a property, but the two distributions do share the same favorable property. The property is, look at any two indices, say x1 and x2, x1 and x3, x2 and x3. In each of these two distributions, they would look the same. Right? So they would look like the uniform distribution on 2 bits. For example, if you kind of...
One column is entirely zero. The bottom
Where?
You meant to do the even strings, right?
Yes. Okay, so I just lied. So let's do it on the fly.
Maybe change the 2 middle x1s to 1s.
So you see here, so any two coordinates you pick, it will be, you'll have like 0, 0, 0, 1, 1, 0, 1, 1 with the same probability, and similarly here, right? And the second distribution, the one I drew on the board, has a smaller support. And we love distributions with small supports. Why is that? Because we don't need many random bits in order to sample from them. Right? So this is kind of the mindset that we should look at kind of what's the minimal resources we need. Kind of, if we only care about the marginal of 2 bits, maybe we can get a smaller support size. Okay? And here's the formal definition. We say x1 up to xn distributed over some alphabet sigma are k-wise independent if for any k coordinates that we pick and any k symbols from sigma, basically the joint distribution look independent. So x restricted on capital I, meaning I1 up to ik, look independent. Right, let's digest it for a minute. And usually, not always, usually, we think of each xi marginally as uniform. So it just means that the probability to see any k symbols marginally is the size of sigma to the power of minus k. Okay. So x sub capital I is uniform over sigma to the k. Okay, so in the language of PRGs, it just says that we can say that G is a k-wise independent generator if the image of G is k-wise independent. Okay, so great, but which curly F's does G fool? So k juntas, meaning functions that only depend on k variables. This is kind of immediate. Also, degree k polynomials is pretty easy to see. Also, this is nice. This is, I think, initial D2 Bazzi. Functions that are sandwiched between 2 degree k polynomials. So say you have a function but you cannot bound its degree, a polynomial, sorry, you cannot bound its degree, but it's bounded between two degree k polynomials in this sense, then you can show, and it's pretty easy to see, that it's full by a k-wise independent distributions. Also, if you know what decision trees are, so also depth k decision trees are full by k-wise independence. And in terms of seed length, that's the seed length we should expect if we just do the counting. Well, actually, it's a bit different here because there are no error right now. There will be, so it does not really fall from the theorem I just showed. But this is optimal, and we'll see a construction that achieves that. Okay. Yeah, let's see one similar construction, and then conclude for pairwise independence. So we want to construct x1 up to xn that fools very simple tests that only look at 2 bits. But actually, even that is pretty powerful. For example, it lets you show that the problem of maximal independence set is in NC, which is the class of parallelizable algorithms. So it seems kind of like very, naive, but already pairwise independence is powerful. So here's the construction. So our sample space is just 0, 1 to the log n. So we'll need log n bits to sample from it. And given a non-zero A from our sample space, how do I generate x1 up to xn? Xi is just the inner product between A and I mod 2. Okay, that's it. If you want to view it as a table, say this row is indexed by A, so you just output A1 mod 2, A2, etc. when I view 1, 2 as the binary representation of those numbers. And why does it work? Because over F2, distinct I and J's are always linearly independent. So each affine constraint shave off half of the entire space. So the probability that for any distinct ij, the probability over the sample space that xi is b1 and xj is some b2 is exactly 1/4. Okay. So I think I'll conclude now. I'll just say what I plan to do in the following 2 talks. So we'll finish bounded independence. I'll talk about more advanced results that use pairwise independence. Then I'll talk about small bias spaces, a bit about Fourier analysis, the technique called random restrictions. Also talk about seeded extractors. And we'll also see quite a lot of expanders, how our expanders are using pseudorandomness. And kind of begin building the toolkit, essentially. So today was more of an intro, and we'll start to see more constructions in the following 2 talks.
So this example is like a code, or it's
A what? Sorry?
a code? Like
Yes.
It's linear, right? It's
Yes.
a Hadamard code?
Yes.
And you're just sampling a random code word?
Yes.
And
So,
so the fact
from the
that it's-
generator matrix, you don't need.
So the fact that it's somehow pseudo-random is somehow saying that the code is separating?
Has large dual distance. More questions? Okay, thanks.
couple of announcements. So one announcement